just like this one also. Okay, it was so long I could not copy any. So I'm very happy to be here, and I must say that what I'm going to present is not exactly in the hardcore of the conference because there is no temperature effect. I apologize, Jason. Jason always complains when I don't introduce temperature in my stuff, but there is no temperature in here. Anyway, you will see at the end that there may be something related to irreversibility. Okay. So first, usual advertisement, but it's serious. If good graduate students who have graduated want to come for a postdoc, we don't spoil them. And when they achieve well, I can tell you they receive good enough recommendation letters to get good position when they go back to their country. I can give you several names. So you are welcome if you are interested to apply. Okay, so a little more of presentation. The people who have worked since several years on Anderson localization and related stuff in our group are first we launched the program with Philippe Bouillet, who is an experimentalist like me, but now we move to Bordeaux. He's the director of the Institut d'Optique in Bordeaux, so if you like good wine and optics, you may ask him to be invited in Bordeaux, he will be happy. And then there are the younger people, the team of Vincent Josse, who worked on 1D Anderson localization and now works on 3D Anderson localization. Then there is a team of Thomas Bourdel, who works on 2D disorder stuff, because he has not yet achieved Anderson localization. And here is a team of theory led by Laurent Sanchez-Palencia, and we have several collaborations with distinguished people. Okay, so I assume that not all of you are familiar with Anderson localization, and when I started this field, I was not familiar at all, so I'm going to tell you my naive view about Anderson localization, why it is interesting. Because at the beginning I knew we could do experiment on Anderson localization, but I was not convinced why it was interesting. So I'm going to tell you why I understand that it is interesting after talking with many people. To make a long story short, let us say that if we consider the classical model of electrons in a disordered medium, they bounce. This is the Drude model. They bounce, and so this bouncing hinders the propagation, and we easily understand that when we increase the amount of disorder, whatever it means, it decreases the conductivity. But there are some circumstances where it seems that when you increase the amount of disorder, not only conductivity decreases, but it's totally cancelled. It goes to zero. And this classical model cannot tell you that suddenly the conductivity can go to zero. This is why Anderson localization was introduced. So the Anderson localization, as it was introduced by Phil Anderson, is presented in the context of the tight binding model of electrons in a crystal. So as you know, in this model, the electron can be trapped in potential wells, but they can tunnel from one well to the next one. And when the tunneling is enough, then you have a so-called extended wave function. Basically, they can propagate. And the way Phil Anderson introduced this order was in having each potential well displaced up and down. So the amount of disorder is described by the spread in the position of the bottom of the potential well. And Phil Anderson demonstrated that when the amount of disorder is large enough, then rather than having an extended wave function, you have a localized wave function, that is to say a wave function whose square modulus has an envelope or has this shape. Okay. So this is a vision of people in condensed matter physics, but I am an AMO physicist, somebody coming from waves, and the way we understand Anderson localization, we people who like waves, is the following. In an homogeneous medium, you can have a propagating wave like that. And now you introduce disorder by introducing small scatterers here. And on each scatterer, you have a very small fraction of that wave that scatters, okay? And when there is enough of this small scatter wave, then you have the same phenomenon, and I am going to tell you a little more about that. So let us consider more in details what happens. There is a big wave, plane wave, trying to propagate in a homogeneous medium, but now we have the scatterers. So we have a first scattering, second, third, fourth, and finally it can come back to the origin by multiple scattering like that. The idea of Anderson localization is that if there are enough of these loops coming back at the origin, all in phase, then there is a constructive interference for coming back to the origin. And this constructive interference, of course, will correspond to, because we have a conservation of the probability or whatever, this constructive interference increasing the probability to return to the origin will correspond to a decrease for the propagating wave. Okay? And this image is not fully rigorous, but anyway, it's very interesting because it can allow us to understand the most important features of Anderson localization, which are indicated here. Before going there, let me speak of the so-called Joffé-Rigol criterion, which says that there is a 3D mobility edge. If you ask yourself the question, is there a simple condition for having all these loops coming back in phase to the origin? And the obvious answer is yes. If each loop is much smaller than one wavelength, everybody comes back in phase, right? So, hence, this condition, if the mean free path is definitely smaller than the wavelength, or better than the reduced wavelength, then a few mean free paths bringing you back to the origin will have a dephasing which is definitely less than 2 pi. And so everybody will come back in phase. It's trivial, but that's it. Okay. This is the so-called mobility edge. So what are the main features? First, Anderson localization is a single particle quantum effect. When I draw all these diagrams, there are not many photons or many particles scattering. It's a single particle. I'm talking of the wave function of a single particle. It's many amplitudes related to a single particle. So we don't have any interaction. Anderson localization is due to the interference of many scattered wavelets. And last and not least, this simple-minded reasoning allows you to understand the crucial role of dimensionality. There are very abstract theorems about Anderson localization, the so-called scaling theory of localization. It's very complicated, very difficult for me. Jason makes all effort to explain me, but I am not good enough to understand. But at the end of the paper, you know that the situation is totally different in 1D, in 2D, and 3D. In 1D, there is always localization. In 3D, you have localization only if you fulfill this condition, and 2D is a marginal case, separating the two situations. Now, if you believe me that this is an end-waving explanation for Anderson localization, you understand the role of the dimension. In 1D, you make a random walk. It's very easy to return to the origin. Okay? In 2D, it's not so easy. Try to play golf at random. How long will it take to go to the hole? Okay? And now try to think of golf in 3D. It would be a nightmare. You have no chance to go back to the hole. Okay? So it's well known that returning to the origin by a random walk is totally different in 1D, 2D, and 3D. So this naive image may not be perfect, but it tells you a lot about the physics of Anderson localization. Now, Anderson localization is so fascinating that people have been trying to observe localization for many kinds of waves. And because I don't have enough time, I'm going again to make the story short. Basically, the reason why it is difficult is the following. Let us suppose that you have an electromagnetic wave, or let's say a light wave, in a scattering medium, okay? And you try to observe Anderson localization. What do you want? You want to have a very short mean-free path. So you want to have a lot of scattering. How do you get a lot of scattering? By putting small particles with a large index of refraction contrast compared to the medium in which you are embedded. And how do you get, or what can't you avoid when you have a large index of refraction contrast? You cannot avoid some kind of absorption. So if now I come and I tell you there is an exponentially decaying profile, you are going to tell me, hey, it's just ordinary exponential decay because you have absorption. So the rule of the game is to show that you have localization and that this localization is not ordinary absorption. This is why it's so difficult. So this being said, it explains why people are really terrible fight in this community, because guy comes and say, oh, I have proven that I have Anderson localization. The other one, no, you have not proven anything. But at the end, to be fair, I think that there are several experiments which are convincing, but you have to understand that it is very difficult to make your point. And so this is why this was to prepare the fact that I'm going to advertise ultra-cold atoms. Well, probably I don't have to advertise too much here, but when I speak in other circumstances, I have to advertise. So ultra-cold atom, many good features. Controllable dimensionality, we know that nowadays we can make 1D, 2D, 3D situation. Wavelengths can be changed in a huge range by controlling the temperature. A very important feature, we can have pure potential. If we make an optical potential with far off resonance radiation, probability to have a spontaneous photon is 1 per minute or something like that. If your experiment lasts less than 1 minute, there is nothing like dissipation. If you don't have any spontaneous scattering, you have nothing equivalent to absorption for ordinary waves. Okay, so we can really be in a situation. We have a controllable disorder. I will show you an example. And compared to condensed matter, many observation tools. You will see an example. We can make photo of the wave function. People in condensed matter can hardly, well, in some special cases, 2D, electron, liquid helium. But usually they cannot make photo of the wave function and many other methods, time of flight, bright spectroscopy, etc. But of course, a new feature. We know that ultra-cold atoms have interaction. And I insisted that Anderson localization is a single particle phenomenon. But Anderson himself said that what would be interesting is to study the phenomena in the presence of interaction. But he did not know how to attack it. So he took the simplest problem, which is without interaction. But when you have interaction, it's yet more interesting. And I will come to that later. Okay, I told you we can make controllable disorder, and I want to advertise my favorite disorder, which is laser speckle. And the reason why I want to advertise it is that it had very bad fame when we started this experimental program. Most of the people told me, oh no, speckle is not a good disorder. But I love speckle because I did a master thesis about speckle long ago. So, you know, first love is always. So I tell you why speckle is a well understood disorder. The reason is written here. Central limit theorem, which is a very good theorem. If you take laser beam, pass it in a scattering plate, which imposes random phases here, now consider the classical electric field that you receive in one point here. It's the sum of the many electric fields scattered from the various places here. So it's a sum of random variables which are mutually incoherent, but which have the same statistical property. As a result, you can apply the central limit theorem, and you know that the electromagnetic field here is a Gaussian process. Of course, the atoms are not sensitive to the electric field itself. They are sensitive to the square modulus of the electric field. And if you are interested in the correlation function of the square modulus, it's a fourth order moment. But thanks to our friends theorists, we know that for a Gaussian process, you can express the fourth order moment as a function of the second order moment. And so we know everything about that. And this has been checked for decades by optics people, that the speckle, really the speckle statistics follow this rule. So we understand well, we can calculate the size of a grain of speckle, that is to say basically the size of the autocorrelation function of the disorder here. And one property I will use later, because the electric field follows a Gaussian distribution, then its square modulus follows this distribution, which means that the biggest probability is for the intensity, which is 0. This will be important at one point, if I have enough time. Okay, we embarked into this subject long ago, not long ago, 5 years ago, something like that. And I just show you the results. There is a lot of interesting things to say there, but I don't have time. How do we do the experiment? The atoms are trapped in an optical tweezer. They can circulate horizontally here, so we are 1D. We apply on it a speckle, which is obtained with we have a diffusing plate, but we have an elongated aperture like that, which means that here, this is the structure of the speckle, but there is also a length around that, so it's just like disks perpendicular to the waveguide here. So for all practical purposes, it's really a 1D problem. Atoms can circulate like that, and they see something which depends only on Z. So you have values here, and what we did, you start with a BEC, you release it, the interaction energy converts into kinetic energy. So if there is no disorder, this is what you observe, ballistic expansion. And if you have disorder, what you observe is that after a certain time, it stops expanding. This is a true photography of the squared modulus of the wave function. It's just an absorption image. For those of you who are not familiar with that, the trick in using a Bose-Einstein condensate is a trick to have in a single shot many times a single particle wave function. We let the BEC expand until the moment when it's no longer interacting. So it's many times the same particle in the same wave function. So we don't have to repeat the experiment 1 million times. We have 1 million atoms. It's just like when I do a diffraction pattern with a laser beam. A laser beam is nothing else than many photons in the same mode of the electromagnetic field. This is why it's so easy to observe interference, diffraction, etc. Here, it's the same thing. So this is a true image of the localized wave function. If you plot it here, you can fit an exponential. If you plot semi-log, I prefer that because when I was a kid, you know, we plot on semi-log paper. So you can see that it. So the students do that for me. They are nice. So here you can see that it is definitely exponential, but the most beautiful result is here. You observe the profile after 0.8 seconds, 1 second, 2 seconds, and you see that really, and you see here what happens. It starts expanding and then boom, it stops. See, 0.8 seconds, 1 second, 2 seconds. Of course, we lose a little bit of atoms, but this is experimental details. Okay, now let us come to the more interesting, or not more interesting, more recent results. 3D Anderson localization. This is really a very important subject because here we have the mobility edge, etc., and you have to know that even for the simple one particle problem, theorists can tell you how the mobility edge scales with the parameter, but they cannot tell you what is a prefactor, for instance. And if you want to know the prefactor, you have two options. Either numerical calculation, very complicated because it's 3D, it's huge, you need to have a very narrow grid because the disorder is, has a short-range correlation, so it's very complicated. Or approximate theory, the so-called self-consistent theory, and there are discussions. Some people love the self-consistent theory, Other people hate the self-consistent theory, so it would be good to make a measurement to know whether or not the self-consistent theory can tell you what is the right prefactor, etc., etc. So here, there is something interesting. So, how do we do the experiment? First, as we discussed this morning, now we have 3D. In 1D, it's easy. You have the atom in a tube, you don't care for gravity. In 3D, you care for gravity. So two options. Go to the shuttle, I'm too old, or compensate gravity. So we compensate gravity with a gradient of magnetic field. There is a residual curvature, and we select the case where the residual curvature will expel the atom. So if we observe localization, people cannot tell you that it is a residual trapping, okay? This has been calculated well enough that we can observe the atom up to 10 seconds. I mean, we release the atoms and we can observe up to 10 seconds, you know, so it's a good system. Now, the second challenge is to create a 3D speckle. Of course, theorists would like that we have an isotropic 3D speckle. Forget about it. What we do is that, because, you know, optical access, etc., okay. So what we do is that we cross two speckles which are mutually coherent. So we add a speckle coming from here to a speckle coming from here, and because it's coherent, I can repeat the argument of the central limit theorem. The guy who is here sees field coming from here for here, and the central limit theorem applies to everything, provided that the polarization are well chosen, which is the case. We choose the polarization along the y-axis, and so you can add this plus that. So it is a real speckle. It's not isotropic. We can calculate, you have here the autocorrelation function, we can calculate. It's not isotropic, but it has a short correlation length in all 3 dimensions of space. They are not the same in all directions, but they are always small. You see, always less than 1/3 of a micrometer in all directions of space. Okay. With this,
what's the wavelength?
What?
What's the wavelength of the?
The wavelength is the usual wavelength for this kind of experiment. Zero. It's red. Okay. 0.78 micrometer. Okay. Well, don't believe that our resolution is fantastic. This is the parameter. It's a radius. It's not a diameter. What you have a pattern, and you fit a Gaussian, and this is the parameter of the Gaussian. So it's half of the height at 0.6, etc. But anyway, it's impressive, okay? So we do the experiment. We know that in 3D, localization will happen only if the mean free path is short enough. So we start with a weak disorder, a small amplitude disorder, and we observe no localization. The cloud expands, and after 1.2 seconds, beyond that, we cannot observe anything. So the cloud expands, and there is no more signal. But if we increase the amplitude of the disorder, decreasing the mean free path, then we see that it starts expanding, but then there is something which stays here for 6 seconds, and we can even see it for 8 seconds. And so something is localized, okay? Related results were observed in the group of Brian DiMarco, but in a situation completely different from ours. In this situation, it doesn't have the crossed second beam, so his disorder is extremely elongated along one direction. Okay, but yes, result similar. Okay, now how do we analyze?
So it's similar result even though he has correlations on.
No, but when I say similar, it's a similar experiment. He has completely different results.
Brian's experiment to come. It's actually not so bad. So he has correlation.
I didn't say it was bad.
No.
I said it was different.
So the laser has correlations, okay? But he doesn't make the axis of the laser propagation one of the lattice axes. So sort of hits one atom and then keeps missing all the other lattice sites, right? And so actually,
why do you speak of lattice? Here we don't have any lattice.
No, it's in Brand.
Okay.
And so because it's propagating along some non-commensurate kind of direction, right? Then actually the correlation, if you look only on the lattice sites, is not long.
Anyway, let us comment on this experiment. How do we analyze that? we have a phenomenological model which does not rely on theory except on extremely simple undergraduate physics theory. We assume that we have a standard diffusion, that is to say Brownian motion, okay, plus a localized fraction. So if this is the case, what do we expect? We expect that the density is equal to, the density has two components, a stationary component plus a component which is diffusing. Here you see that it is only 2 dimension and not 3 dimension. Why? Because we are making absorption. So what we measure is column density. Column density means we integrate along one direction. So we integrate along x, okay? Now, what do you expect for the diffusion? If you have integrated along one dimension, you expect an evolution as 1 over t. Because it would be 1 over t to the 3/3, to the 3/2 in 3D, but because we integrate along one direction, what is left is 1 over t. So we are going to fit our density at the center here by a curve which is something in 1 over t plus a constant. In the first case here, the constant is 0, so no localization. In the second case here, the constant goes to a certain value, and this gives us a value of the fraction which is condensed, which is localized, sorry. So this is a phenomenological analysis which I think is very convincing. Now, what else can we measure? Well, if we just plot the square of the mean square, the radius, or the mean square dimension versus time, we see a linear evolution, and this gives us directly the diffusion coefficient. So we can measure the diffusion coefficient as well here as here. Diffusion coefficient of what here? Of the not localized fraction. So we measure all that. This is a pure, very simple analysis. Okay, no theory in that. Yes?
So, what is blue and red in the
blue and red, it's because it's not isotropic. So we don't have the same coefficient along the two axes, x and y and z. Okay? So this is a case, this case, diffusion coefficient is large, expands rapidly. Here, in the second case, diffusion coefficient is small. Now, the theory is complicated. It has been done by a theory group. It's okay. There is still something to understand. They have to put by brute force an adjustable parameter, which is, there is only one adjustable parameter, but anyway, there is an adjustable parameter. It tells them that there is something to understand, and I think they are understanding it. This is their paper. Okay. What I want to do now is to speak of something slightly different in a few minutes. What we have observed, there is no doubt, is a localization that cannot be explained by classical trapping below the classical percolation threshold for the reason I explained you. With the speckle, there is a lot of places where the intensity is very low. So there is always a probability that a classical particle escapes. So if you observe that it does not escape, it cannot be understood by the fact that there are mountains and you are trapped between the mountains. Cannot be understood by quantum trapping in local minima of the disorder because there is no trapping level in these local minima. They are not high enough. Okay. So how can you explain it if it is not by Anderson localization? So it's hard to conclude that it is not Anderson localization. Anyway, Anderson localization is about a fully coherent phenomenon, coherent addition of many amplitudes, and we would like to have a smoking gun of the coherence. And for that, we went back to something which has been known for years as weak localization, which is not as sophisticated as Anderson localization, but which is a precursor for Anderson localization. What is it? It's coherent backscattering. So you will understand what is coherent backscattering, but I first describe the experiment. Now we have only one beam like that. It's a 2D speckle, which means we have elongated structure like that, and this is a cut of this structure. So you have to think of it like bars like that, and we are going to launch the atoms perpendicular to these bars. So it is a 2D problem. So I have bars like that, like a pachinko, okay? So I launch the balls, the atoms here, and they are going to bounce like that. The difficulty of that experiment and the beauty of that experiment, which has been done by very, very smart students, is to make an initial distribution of momentum extremely narrow. I can explain later how they do it, but this is the measure initial distribution of momentum directed along Z, along the Z axis, with a narrow distribution. So we launch the atoms here. Now, after some time, we switch off everything, oh, not everything. We switch off the disorder here, but we leave the suspending coils, and we observe the time of flight, which means that after a long enough time of flight, we have a momentum distribution. Again, beautiful tools. And here, the tool is very beautiful because we can observe the atom for many seconds. So the resolution in velocity, in momentum, is excellent. And now, look at the result. Time t equals 0, we launch the atom like that. This is a velocity distribution. Okay, after 1 millisecond, you start seeing a circle. Why a circle? It's elastic scattering. You conserve the kinetic energy. You conserve the modulus of the momentum. So you have elastic scattering on a circle, and then you see a peak in the backward direction. This is a coherent backscattering peak, which is still there when you have totally lost the memory of the initial direction that is beyond the Boltzmann time. You have this peak here. This is coherent backscattering. This is a fully coherent phenomenon, and I explain it in a few words. And the reason why I like to explain it is that I can make a full theory of that with a notion that I was teaching this guy when he was an undergraduate. Only Brownian motion. You can calculate everything by Brownian motion. What do you have? Coherent backscattering is an interference between this scattering process and that scattering process. You have a plane wave arriving like that and a plane wave going out. You must add all the various amplitudes, and if you add this one and this one, they will interfere, but with a phase which is which has no particular value, except if the PF equals minus PI. If PF equals minus PI, then the phase here and the phase there are exactly the same, and so you have a reinforcement in the backwards direction. You have an amplitude, so you have a factor of 2 increase. Now, once you have understood that, if you want to calculate the width of the peak of this coherent backscattering, what do? As I say, simple Brownian motion. The distance between here and there spreads according to a usual diffusion law. And once you know this distribution, you just take the Fourier transform and you have the width of the peak. Really elementary undergraduate physics. This is the result, sorry, this line is the result of the calculation. Look how beautiful it is. I'm done. Of course, you are going to tell me here doesn't work. Of course it doesn't work. Here, the time is too short to have 2 scattering. It's single scattering. With a single scattering, you don't have coherent backscattering. So here, of course, you have to be a little more sophisticated, and as usual, you start making a theory, and finally you find a paper by a Russian 50 years ago, or 30 years ago, or 40 years ago, who has done the calculation, so we use it, and it works. Yeah, sure. Visibility, this is a simple theory. Why is it less? It's less because it's not truly 2D. I have bars like that, and after some time, goes on the side like that. It's not, we don't confine we should confine our atoms, but we did the experiment that way, so we understand that also. Okay, I finished. Just, I want to say that What would we like to do? And I only speak here of this last experiment. We would like to have more evidence for the role of coherence. And in optics, there is one thing which is well known, which is breaking time reversal invariance. That is to say, you have the two loops, and you would like to have the two loops not equivalent. In optics, they apply a magnetic field on a Faraday medium. Can we do something like that here? Of course, there is all this new domain of artificial gauge field. There may be a simpler way, which consists of shaking the potential. Because the loops are, the atoms or the amplitudes are going slowly along the loops, if we shake the potential, it's not the same this and that. Maybe these are ideas. We need support from our friends theorists. So to conclude, when we do all that, do we have a quantum simulator? Well, I hope my friend theorists forgive me for this joke. At least I am sure it will be a quantum theory simulator. Thank you very much. Thank you very much.
Questions?
In one of the prior, you showed this localized fraction as a function of
Yes.
This speckle intensity.
Yes.
Right. And then the theory curve seems to show kind of downturn when the speckle intensity gets pretty strong. How do we understand that?
Well, we don't, honestly, we don't understand well it, but the most, if you allow me, because you asked this question, I want to comment on something else. Why is it that we never have more than 22 or 23% of localized? It's because of the way we do the experiment. The way we do the experiment, we let the atom expand, and then we switch on the disorder. When we did that in 1D, we switched off a weak disorder. So basically, it doesn't affect too much the energy. But here, because of the mobility edge, we must switch on a large enough disorder. And so we provoke a big energy spread. Okay? And this big energy spread, we have studied that, the theorists have studied that, is such that there is always a fraction of the atoms above and a fraction of the atom below. So the next challenge for us is to be able to operate differently so that we can have the atoms in the disorder with a well-defined and a well-controlled energy. So what we demonstrate here is that there is always a localized fraction. I think it's good enough. It's a first demonstration that there is a localized fraction. But if we want to study precisely around the mobility edge in order to measure the mobility edge and look for critical exponents and stuff like that, then we have to be able to have a thin energy distribution that we can vary around the mobility edge, and we are working hard at that. It's not easy, but probably we are going to succeed.
Why don't you turn on the random potential first and then expand it? Why do you have to turn it? Why do you let it expand and then turn it on?
Well, this is another option, of course, putting the disorder and let expand. Again, this method will not allow us to control the value of the energy. And we tried, we don't have any impressive result. And anyway, let us suppose that it works. How are we going to control the value of the energy compared to the mobility edge, etc.? So we are trying something else. And don't tell us about adiabatic turning on the stuff, because then I would not understand exactly what it would mean. Can we cross a quantum phase transition by doing an adiabatic ramping? I doubt it, etc., etc.
So just to understand precisely, so the fraction of localized atoms
20%.
is, you believe is the fraction of atoms that have wavelength longer than the
and energy smaller.
Exactly. And you're saying an energy smaller than the potential height, or are
No, not the potential height.
Right.
Smaller than because the mobility edge, I think of it more as a value of an energy than a value of a wavelength, because the wavelength is not so well defined in the disorder, okay? So I prefer to think of an energy. I think the energy, for me, an energy is a better quantum number than the wavelength in a problem where the eigenstate of the Hamiltonian are not eigenstate of the momentum, okay? So this is why I prefer to speak in energy.
But the potential height is something completely different.
Yes.
Here, right?
No, this is why it is important to realize that in 3D, I will draw it in 2D, but the situation is we have many peaks like that. The mobility edge is somewhere here, that is to say, below the highest peak. But anyway, because of these properties that the distribution of intensity in a speckle has a maximum value for 0, there are many valleys and all the valleys are connected. This is the important point, that all the valleys are connected. So the mobility edge is here, but the bottom of the valley is well below. Now try to extrapolate this image in 3D. I can't, but you understand what I mean. So this is exactly the situation. In 1D, the situation was totally different. In 1D, we were ramping a potential which was always less than the value of the energy. But in 3D, this would not lead to any localization. A localization in 3D demands that the height of the peaks is larger than the value of the energy of the atoms. You know, hand waving is useful.
All right, let's thank our speakers.
Thank you.
All right, our second talk is Maxim Bashani, and he's going to talk on integrable, one-dimensional, three-body problems based on exotic and non-crystallographic root systems.
Oh, you want a microphone? Well, Maxime, you can speak loud, right? I don't know. Sorry for One, two, three.
Right, so similar to Brian Anderson's talk, I'm going to spend quite a long time in introducing things which are not generally familiar to the audience, so less familiar subjects. And so we're going to deal with two domains of knowledge. So one is famous in mathematics, the so-called root systems. Another is n delta interacting particles in one dimension. And so we are going to, more to the point, we're going to concentrate on two-dimensional root systems and three delta interacting particles in one dimension. So we're going to bring these two domains together and see what the interface between them is. And then, of course, I mean, you can see it's a Newton cradle, but now a Newton cradle with balls of different masses. So that's the important ingredient. So in particular, if you have a Newton cradle with one infinite mass, one mass 3 and one mass 1, this realizes the root system which is called G2. Or if you take two equal masses with this strange mass ratio and so forth, and mass 1, this is another root system, which is called I to 10. But the funny thing is that if you plug the actual masses in, so the mass ratio will be pretty close to to a set potassium 40 lithium 6, and so we'll see in the end that there are a few mass combinations that by accident realize what we want. And what we want is really a root system. And
Maxime, I can't do the roots in my head. How close are these?
Who?
The square root of how close is this? You know.
How it's within 1%. But I'll show another example where it's less. Within 1%. So I will show one example where it is within 1/10%. So it's 0.8%, and that's my favorite example. Not this one, the other one. So no, those are the numbers are no. It's numerology. No, I'm not claiming nature. What?
Like your talk has exact in the title, so for you 1% is infinitely far away.
Oh, right. Well, there's also always a width. I mean, for any effect you have a width, and the question is, well, right? But that's.
So if you are a lousy experimentalist, it's not infinitely far.
Right.
Depends on the quality of your experiment.
And so the origin, the historical origin for this project is one phrase I read in a famous book on beta ansatz by Michel Godin, who analyzes the relationships between integrable many-body systems and kaleidoscopes. And kaleidoscopes are systems of mirrors that relies on the finite number of reflections and so on and so forth. And so kaleidoscopes are very important in mathematics because some of them, namely the crystallographic kaleidoscopes, they allow you to classify the Lie groups and so on and so forth. So what he said was that there are classic root systems which are interesting, which are important to us physicists, and exceptional or exotic. They're not physical at all. And I, being pretty attentive to details, let's call it that way. This phrase really bothered me for a long time, but for almost 20 years. And so, to briefly give you the history, to briefly explain why I'm introducing something that appeared in the early 60s and was mainly developed in the early 60s. So let me show you how the effects I'm going to present could have been overlooked and why they were overlooked. So the story of the relationship between the root systems and integral models really starts from Girardot's model. So those are n hardcore bosons in one dimension, and they give you an n hard boson realization of what would be called an an minus 1 root system. So then in '63, Liebling generalized this model to finite strength interactions. Later, McGuire and Godin analyzed to finite strength interactions in many details, and they gave what might constitute the proof that this A system is the only one that is relevant to finite strength interacting bosons. And so my theory that the field of mathematical physics was so excited with finite strength delta interactions that they forgot about the hard cores. They forgot to actually explore the whole area of the hard cores. And so in 2013, I'm returning to hard core, not bosons, hard core particles. So those are different masses. They have different masses in general, and thus neither bosons nor fermions. So let me briefly tell you what root systems are. They're immensely important in mathematics. And actually they're used for almost everything. So what is the root system? So it's a collection of vectors. First thing it does is so if it's a root system in a d-dimensional space, it's a collection of vectors that spans the space. This is easy. Then for a given direction, there is a given vector, and it's negative. If those are only two vectors that are allowed along a given direction. So namely, along a given direction, they have only one length. So a more important property is that this set is, if I start building mirrors whose normals are my root vectors, then this system of vectors is closed about these mirrors. So this you can see where kaleidoscopes come in. And the last property, which is less trivial, is that if I compute a difference between a given root vector and its mirror image with respect to one of the mirrors, this difference is going to be integer multiple of the actual normal that was used to generate this mirror. And this property turns out to be important for being extended to periodic boundary conditions. So that this last property allows you to actually build periodic sequences of mirrors. So now, as I said, they're immensely important in the world of mathematics. It's a whole universe. It allows you to classify the simple Lie groups, which is a big part of the modern mathematics. And this is not what we're considering today. So we're considering today a much simpler application of the root systems. So they are used here to generate exactly solvable Helmholtz type problems. And Helmholtz problems, it's just a free particle, so a free quantum particle, so kinetic energy plus this is your energy, but with no trivial boundary conditions, so with some boundary condition on a polygon, and the boundary condition relates the normal derivative, normal gradient of the wave function to the wave function itself. And then the coupling constant that's a technical detail, it can take at most two possible values, depending on whether the given root is. So only two possible values. We'll discuss that. So, and the way root systems come in is that so these polygons, they're nothing else but they're built out of mirrors, which are normal to the roots, and so if a very important property also of the mirrors built by the root systems is that these polygons, they tile the space if you flip these polygons about their own sides, which is a highly non-trivial property. So they cover the space if they flip about their own faces generally. And so, and I won't explain the whole, the mechanics in all details, but the integrability of these polygons, it has three ingredients. So first it indeed this flipping tiling property. Second, you use the method of images to solve this problem. So you flip and repeat your solution with a given plane wave. And the third thing is a Young-Baxter phenomenon that basically says that the result of this operation won't depend on the order in which you've hit respective mirrors. And so remember, there is a coupling constant that is going to become our strength of the delta function. And so for a different coupling constant, you get different solutions, and I couldn't resist. I'm showing just because I like it. So that's that. These are hardcore bosons. These are going to become hardcore particles. So you see there's an exact node at the mirror, and these are finite strength interactions, but not actually particles. So it's just a triangle billiard so far, and it's not going to become three particles. So now, as with any nice set of axioms, you may start thinking about what happens if you remove one of them. And the most natural axiom to remove is to remove this axiom of periodicity, this axiom that leads to that leads to periodic sequences of mirrors. And what you are left with is in fact two mirrors that are not extended to anything periodic, but still, so you can help a problem in between these mirrors. And in particular, this one is an important, this one is a symmetry between two mirrors with an angle between them pi over 5. And this symmetry is if you look at the famous mosques in Spain, so what you see on the ceiling is exactly this symmetry. And also it's a symmetry of most popular symmetry of quasi-crystals. And here it's the same thing, but even nicer. So while alcove is a polygon that tiles the space by flipping, while chamber is a wedge that tiles the space by flipping. So it has one open side. And so that's precisely what it does. So not related to today's discussion, you can also think about removing the second axiom, but not the fourth. So the fact that all routes along a given direction have the same length, and this is tightly related to the classification of the collaborator-Sutherland models. So particles with interactions 1 over r square, and this is not for today. And finally, just to tell you how many of these root systems we have. So there are 4 which are called classic. So A is basically a symmetry of tetrahedron related to n delta redirecting bosons. B, C, and D is a symmetry of Q cube, and this is related to delta interacting bosons, which was also strange interactions where not only particles with the same coordinate interact, but particles with 2 opposite coordinates interact. And this is also not quite physical. So there are exceptional root systems. So G2 is related to well, to nothing. It just exists in 2 dimensions. To a nice triangle with the angles 90, 30, 60. F4 is a symmetry of the only exceptional platonic solid in 4 dimensions, which is called 120 cell. And these 3 are real monsters, and that they correspond to nothing. They don't even correspond to platonic solid. So H's are, so I's are just symmetries of a wedge with angles pi over n between them. And BC, we're not discussing it here. So and so what we discussed today is G2 and this I system. So all 2 dimensional. So what about particles? So while Helmholtz problems we discussed, they live inside polygons, so they are problems with boundary conditions. So they're sitting inside some closed surface, and there are boundary conditions on the surface. What we have with particles is different. So what we have with particles is, in fact, so first of all, so we start from 3 particles, generally with n particles, with some masses. You can always transform your coordinates, so you can always eliminate the center of mass motion of these 3 particles. So what you will get for the relative motion is a particle of a given mass, abstract, in 2 dimensions, that interacts with 3 regions of delta functions. So it really lives in a 3-dimensional space, or in a 2-dimensional space, and so there are 3 lines of a delta function, and these delta functions, instead of introducing boundary conditions, they introduce what is colloquially called the jump condition. So it's a because you approach your wave function, say, approaches this surface. It has this some value of a gradient of the wave function on this side. The gradient of the wave function is allowed to jump on the other side, and this jump is related to the strength of the delta function on this line. And so the art well, actually the essence of the beta ansatz, the essence of all the integrable problems with delta interacting particles is to, in fact, to map this situation to the Helmholtz polygons, to the polygons solvable by via root systems. And there are two ways how one can map to another. So one way is this. Oh yeah, okay. So right, and this is what happens with periodic boundary conditions. Sorry, okay. So with periodic boundary conditions, you get periodic lines of delta functions, and now instead of each sector, instead of each domain, each sector correspond to a particular order of particles. All we can only say is the so each sector would correspond to a particular parity of the ordering of the particles. So for delta functions, for periodic boundary conditions, what you get is three periodic size sequences. So now, so two things must happen, as I said. So one is these lines of the delta interactions should form a corresponding either wild chamber or wild alcove. So one of these polygons generated by the root systems. So the second thing that should happen is that these jump conditions must map to the conditions to the boundary conditions on these Helmholtz polygons. And this could happen in two different ways. So one way is well known, again, since 60s. So you concentrate on particles of equal mass. So you assume that they're bosons. So thus the wave function is going to be symmetric with respect to the flips. And if your wave function is symmetric with respect to the flip about the particular delta ridge, you can relate the gradient. You can relate the gradient of the wave function on this side to the gradient of the wave function on that side. And since they are related, it generates effectively a boundary condition for the gradient of the wave function on the inner gradient of the wave function just inside the particular polygon. So this is. We relate these two, and thus it constitutes a boundary condition for the gradient on the inner side. And this is precisely what happened with the Lieb-Lininger condition on the 60s, in the 60s. But there is another way. So and the other way is this. So you can simply so you can only concentrate on hard cores, and for the hard core boundary conditions, one inner side of the polygon doesn't talk to the outside of the polygon, and thus, well, psi equals 0 is a psi equals 0. So it can be considered as both as a boundary condition and as a jump condition. So the system inside the polygon doesn't know about the outside, which also means in particular that some combinations of masses, they can be integrable for one order of particles, but not integrable for another. And that's precisely what happens. That's precisely what not in this case, but there was some other. Yeah. So in this last case, this is precisely what happens. So and that way we can identify two cases. So one is relatively trivial. So two particles of the same mass at a hard wall, so they can still interact via a finite strength delta function, but plus a hard wall. And the less trivial case is particles of masses 3, 1, and infinity, and a hard wall, and this thing can be even put on periodic boundary conditions and also solved with that. There's another case. So here we have to release the condition that this polygon is closed. So it's just thus here we have to work for integrability. We have to work in the open space with no periodic. We should have to release periodic boundary conditions, and there for each magic angle between two mirrors, for each integrable case, which is which is parameterized by this integer n, there is a continuous family of mass ratios, which of course, so that's where numerology starts, right? So you have a sequence of integers, and for each sequence of integers you have a one parametric continuous family, and well, we have many atoms, even more pairs of atoms, right? And so you could find something interesting there. And
can all these cases be generalized beyond 3 particles as the first case?
No. That's precisely the thing. I mean, this is, I think, I mean, mathematicians would say I explored all the root systems. No, there's no generalization. So we'll talk about many-body later, right? But as an exact effect, I do believe this exhausts everything. And so right. So for hard cores.
The first one can. The first one you can.
First one, actually, first 3 can.
Yeah.
No. First one can. Yeah, first one can, and the rest of them no. So now for well, actually this one right. So. Right. And now let's concentrate on the last case. So again, 3 particles in 1 dimension with magic mass ratios. And how more esoteric can it be? So, but first of all, let's see if we can get these mass ratios. So I consider 2 different cases. So in one case there are 2 heavy and one light particle. So and there are two combinations. So one is lithium-7 cesium, and another is lithium-6 and potassium. So and they realize I2-6 and I2-10. So another case is 1 supermassive or a wall, and 1 light, one heavy. So there is root system 8, and this is sodium and cesium. And now, the following idea. So, of course, nobody, I mean, no experimentalist in his or her right mind would make an experiment with 3 particles, especially that it's not. No, wait. What? What with 3? What did I say?
Selim does 1, 2, 3, 4, 5, 6.
Oh yes. Sorry. Yeah. Okay. Right. Not.
It's clearly not in his right.
But now let's look at what the actual physical effect is. And so the actual physical effect is it's better to illustrate on something which is even simpler than what we discussed. So that's the example of what's called a corner reflector, and all of us know particular manifestations of corner reflectors. So typically it's 3 mirrors at 90 degrees between them, and the property is that when you shine light on them from any direction, so the light entirely returns to the same direction. And then on my walk to here, I found one experimental demonstration for that. As you can see, I mean, this is a reflector from some bike reflectors I found on the street, and I can turn it around, but the light completely returns to the origin, to the laser.
So it's under some localization.
No, not quite. But this is not the effect we're interested in. We're interested in something much simpler than that. So what I want to concentrate on is that I have 3 mirrors here, but the outcome, the outgoing beam, its direction does not depend on the order in which my light beam hit these mirrors. So in principle, and so let's see these 3 mirrors for the radar. In principle, the result should depend on whether my sound wave hit here and then here and then here, or here, here, or here. But for the magic angles between the mirrors, the so for a given direction of the incoming beam, the outgoing beam goes in a single direction, and this is the property which we're interested in. So that's precisely what I wanted to illustrate. So so these two mirrors 90 degrees, they would correspond to something, well, very simple. So let's consider two situations, one generic, one not. So it's super simple things. So one massive particle, but not in finite mass. Two particles of the same mass and smaller, and for simplicity, these two particles don't even interact with each other. So generally speaking, the outcome will depend on whether a faster particle have hit the massive particle first, or the slower particle have hit the massive particle first. So the outgoing momentum distribution for the same initial momentum distribution, which is these two peaks, will have two different momentum distributions. So depending on the order in which these two collisions happen, depending on whether the fast hit first or the slow hit first. But if we nail our massive particle with the nail, and or give it an infinite mass, so we'll get one of the magic angles between the mirrors, and what will happen is that the outgoing momentum distribution won't depend anymore on the order of these two collisions. They will just flip their velocities, and so we'll get the same result regardless of the order. So one would expect that in a more complicated situation, in a particular three-body collision, the entropy increase in the integrable case per three-body collision is less than the entropy increase per three-body collision in the generic case. And so what we did, so first of all, we took indeed the truly honest to goodness integrable case of masses 3,1 and infinity with periodic boundary conditions, and compared it with a generic case which is right in between two integrable cases. So these are the mass ratios, and well, no surprise. So in the integrable case, entropy increase of the entropy, and entropy in this case is just the how uniform the orientation of this relative motion velocity is. So some measure of ergodicity. So entropy stops somewhere short of the absolute of the ergodic limit. So in this case, it keeps growing. So there is no much surprise here. But now, so now what we do is this. So we take something which has a few integrable angles in it, put it in periodic boundary conditions, thus spoiling integrability, but still keeping. So in some three-body collisions, we still have integrable angles, and compared with something generic. And so what we see is that in this case, that is not exactly integrable, but some three-body collisions happen at integrable angles. Entropy increase is much slower, and so the expectation is that if we simply, as Jason said, I mean, if we simply take this mass combination and look at the many body system, we'll still have a slowdown of thermalization at integrable angles, and this is exactly the plan. So, but already already at this level, you can see that the actual integrability doesn't matter. What matters is integrability at the level of individual three-body collisions, and this I'll skip. So many thanks to collaborators. So this part of this work is done by the graduate student Frank Kao, who's here in the audience, and Stephen Jackson is our colleague from mathematics, and it was supported by NSF, ONR, and EFRAF, like Alain. And thank you very much.